Far beyond the blue horizon of our world, a silent sentinel drifts through the absolute cold and darkness of deep space. This magnificent golden eye was designed for a single, profound purpose: to gaze backward into the dawn of time itself. It traveled 1,000,000 miles from home, seeking a lonely, stable point where it could stare, uninterrupted, into the cosmic past. We call it the James Webb Space Telescope, but it is truly a time machine built of mirrors, wires, and human curiosity. Its mission was to answer our oldest questions about where the universe came from and how the first stars began to shine. We expected to find clarity, to see the first galaxies as faint, simple smudges forming in the primordial emptiness after the Dark Ages. But the universe is rarely so simple, and its secrets are not given away so easily, even to our most powerful instruments. Instead of providing simple answers, this golden eye opened 1,000 new doors, each leading to a deeper and more beautiful mystery. The first light it gathered was not what we expected, carrying signals that challenged the very story we told ourselves about creation. It revealed a cosmic dawn that was far more brilliant, more complex, and more baffling than our theories had ever predicted. Let us journey with this silent observer to witness the new enigmas that have bloomed in the darkness between the stars. The first great mystery concerns time, and the impossible maturity of the things that Webb found hiding in the cosmic dawn. Our models predicted the first galaxies would be small, chaotic, and disorganized collections of young, hot, primordial stars. Instead, Webb peered back 13 billion years and found galaxies that were already massive, structured, and surprisingly well-formed. It was like finding a fully grown ancient tree in a garden that should have only contained the first sprouting seeds. These galaxies are far too large and appeared far too early to fit neatly within our understanding of cosmic evolution. The universe, it seems, learned how to build grand cosmic cities much faster than we ever thought was possible. This finding doesn't just add a new chapter to our book of the cosmos, it asks us to reconsider the first page. How could such complexity arise so quickly from the quiet aftermath of the Big Bang? This is the first new question. The telescope then turned its gaze from the grandest scales to the smallest, focusing on the worlds orbiting other stars. It has the power to taste the air of these distant planets, analyzing the starlight that passes through their alien atmospheres. Here too, where we searched for familiarity, we were greeted with yet another layer of profound and beautiful mystery. On one giant gas planet, a world we thought we understood, Webb detected clouds not of water, but of fine silicate dust. Imagine a world where the clouds are made of sand, where it rains molten glass through an atmosphere of crushing pressure. This was not predicted by our models, showing how little we truly know about the chemistry of worlds beyond our own. The telescope did not just find strange new things, it also found an absence of things we expected to be there. On a planet called TRAPPIST-1c, a world once thought to be a candidate for life, Webb found almost no atmosphere at all. It is a bare, silent rock, scoured clean by the stellar winds of its parent star, a ghost world in the void. Each new atmospheric reading, each chemical fingerprint, adds another shade of complexity to the gallery of known worlds. The mystery is no longer, are there other worlds, but what unimaginable forms can a world possibly take? Webb also looked closer to home, into the beautiful, chaotic nurseries where new stars are being born right now. With its infrared vision, it can pierce through the dense clouds of gas and dust that hide these stellar cradles from view. It showed us the famous pillars of creation in a light never seen before, revealing countless infant stars burning within the dust. But within these images lies another subtle mystery about the very first moments of a star's ignition and planetary formation. We see jets of matter shooting from these protostars with unexpected complexity, twisting and turning in ways our physics can't fully explain. These are the birthing pains of new solar systems, and they are more dynamic and more intricate than we ever imagined. It seems the process of creation, on every scale, from galaxies to stars, is far from a simple and linear process. The universe is not just a quiet, stately machine. It is a place of wild, beautiful, and sometimes unexplainable creativity. Even the death of stars has been cast in a new mysterious light by the penetrating gaze of the telescope. It captured a stunning image of a star-going supernova, the final, violent explosion that seeds the cosmos with heavy elements. Yet within the expanding shroud of gas, it detected molecules and dust formations that should not have been able to survive the blast. How does cosmic dust, the raw material for new planets and life, endure one of the most destructive events in the universe? This is another profound question, a puzzle about cosmic resilience and the persistence of the building blocks of everything. The Webb Telescope is not just an instrument of observation, it has become an engine for generating new and better questions. It has shown us that the map of the universe we held so confidently has vast, unexplored continents of ignorance. Each photograph it sends back across the void is a beautiful reminder of how much more there is to learn. We are like children standing at the shore of a cosmic ocean, and Webb has just revealed how much deeper that ocean truly is. The new mysteries are not failures of the mission, they are its greatest and most profound success. They invite us to be humble, to be curious, and to continue staring into the magnificent, star-filled darkness. Now, let us delve deeper into these cosmic enigmas to fully appreciate the strange new universe that Webb has unveiled. One of the most startling revelations centers on what astronomers call impossible galaxies. These are objects observed at a redshift corresponding to only 500 million years after the Big Bang. According to established cosmological models, this is simply not enough time for gravity to have collected enough matter to form such massive, well-structured spiral and disk galaxies. We are seeing cosmic architecture that should have taken billions of years to build, standing fully formed in the universe's infancy. This paradox forces us to reconsider the fundamental drivers of galaxy formation, or even the timeline of the early universe itself. The mystery of these early galaxies is deepened by the supermassive black holes discovered at their centers. The seeds of these gravitational monsters should take immense spans of time to grow by consuming gas and stars. Yet Webb has found fully grown behemoths, billions of times the mass of our Sun, presiding over galaxies that are themselves infants. How did these black holes grow so big, so fast? Some theories now propose direct collapse black holes, which formed from primordial clouds without a star phase. But this radical idea itself opens a whole new set of questions about the universe's first moments. Beyond grand structures, Webb's spectrographic analysis of exoplanet atmospheres has revealed a chemical zoo that defies easy explanation. On the hot gas giant WASP-39b, it found definitive evidence of sulfur dioxide. This molecule is created by photochemical reactions, meaning the light from the parent star is actively and unexpectedly rewriting the chemistry of the planet's atmosphere. This discovery implies that alien skies are not static environments, but are dynamic chemical laboratories, where starlight creates exotic compounds we have yet to imagine, complicating our search for simple biosignatures on other worlds. The telescope has also brought the enigmatic brown dwarfs into sharper focus, and with that focus, more mystery. These objects are failed stars, too small to ignite nuclear fusion, but far more massive than planets. Webb's infrared sight revealed one such brown dwarf with clouds made of silicate vapor, essentially fine, hot sand. This suggests a weather system of unimaginable scale and violence, with swirling clouds of rock and rain made of molten glass. It forces us to expand our definition of what a planet or a star can be, revealing a vast and strange middle ground between them. Another perplexing discovery lies not in what Webb found, but in the cosmic dust it can see with unprecedented clarity. The telescope has observed very old, distant galaxies that are inexplicably dusty. Cosmic dust is formed from heavy elements forged in the hearts of dying stars. To have so much dust so early in the universe suggests that the first generations of stars must have lived and died on an incredibly accelerated timeline, far faster than our theories allow. This early dust problem challenges our entire understanding of the life cycle of the first stars and the chemical enrichment of the cosmos. When Webb pointed its mirror at Stephan's quintet, a famous compact group of 5 galaxies, it did more than just take a beautiful picture. It peeled back the veil on galactic evolution in action, revealing shockwaves and tidal tales of gas and stars being ripped from one another in a slow, cosmic dance. Most mysterious are the vast nurseries of star formation triggered by these collisions. The data shows star birth happening at a rate far more efficient than expected, hinting that our understanding of how gravitational chaos can trigger creative processes is still surprisingly incomplete. The telescope's infrared eyes have also captured the clearest view yet of the center of our own Milky Way galaxy, a region shrouded in thick dust. While it has not imaged the central black hole directly, it has tracked the motion of stars orbiting it with incredible precision. These observations have revealed subtle deviations in their orbits that are not fully explained by the black hole's gravity alone. This hints at the presence of unseen structures, perhaps clusters of smaller black holes or concentrations of dark matter, creating a new puzzle right in our own cosmic backyard. One of the great quests for Webb is to study the first stars, the so-called Population 3 stars, forged only from the hydrogen and helium of the Big Bang. While none have been seen directly, Webb found a galaxy whose chemical makeup suggests it contains a cluster of these pristine, mythological stars. The light from this galaxy is dominated by helium emission, with a surprising lack of heavier elements, fitting the theoretical profile of a place where the universe's very first suns are still burning. Finding this is like finding a living fossil from the cosmic dawn. The concept of the cosmic web, the vast filamentary structure of dark matter upon which galaxies are built, has long been a theoretical model. Webb has provided the first direct observational evidence of this web in action. It captured an image of a distant quasar whose light illuminates a colossal 10 million light-year-long strand of gas flowing into forming galaxies. We are seeing the cosmic plumbing of the universe, the invisible highways that funnel raw material to build the cities of stars, and its structure is more complex and clumpy than simulations predicted. Webb's study of ice and organic molecules in the coldest, darkest molecular clouds has also yielded surprising results. It found that complex organic molecules, the potential precursors to life, are far more abundant and varied in these stellar nurseries than previously thought. It has detected complex ices containing not just water, but methanol, ammonia, and more. This means the raw ingredients for life are not rare, but are common components of the celestial soup from which new solar systems are born, deepening the mystery of why life hasn't been found elsewhere. In a remarkable use of gravitational lensing, where a massive galaxy cluster bends the light of objects behind it, Webb observed the most distant star ever detected, named Earendel. This star existed when the universe was less than 1 billion years old. The mystery is its sheer mass and temperature, estimated to be over 50 times that of our Sun. Such massive stars should be exceptionally rare, yet we found one through this chance cosmic alignment. Is this a statistical fluke? Or were the first generations of stars routinely more gigantic than the stars of today? Another profound enigma has emerged from observing the rate at which the universe is expanding, a value known as the Hubble constant. Measurements from the early universe and the modern universe have always disagreed slightly, a problem called the Hubble tension. Astronomers hoped Webb's precise measurements of distant stars would resolve this. Instead, its data has confirmed and sharpened the discrepancy. This suggests there is not a simple error in our measurements, but a fundamental piece of new physics missing from our model of the entire cosmos. The telescope has examined the empty spaces between galaxies, the so-called intergalactic medium. Far from being empty, these voids are filled with a thin, almost undetectable fog of gas. Webb's sensitivity has allowed it to study this fog in detail, revealing unexpected clumps and chemical signatures of ancient, exploded stars. It seems the voids of space are not voids at all, but are repositories of cosmic history, haunted by the ghosts of long-dead galaxies, a discovery which complicates how we account for all the matter in the universe. In the atmosphere of the exoplanet, K2-18b, located in its star's habitable zone, Webb made a tantalizing detection of a molecule called dimethyl sulfide. On Earth, this chemical is produced almost exclusively by living organisms, specifically marine phytoplankton. While this is not definitive proof of life, it is a stunning and unexpected discovery of a complex biosignature on a world over 100 light-years away. It presents a profound mystery. Is this a sign of alien biology, or is there an unknown geological process that can mimic the chemical breath of life? The Southern Ring Nebula, the beautiful, expanding shroud of a dying star, was imaged by Webb in breathtaking detail. The images revealed that the central star, long thought to be a single entity, is actually a close binary pair, with one star hidden in the dust. This hidden companion has been shaping the nebula's intricate structure for thousands of years, carving out the patterns we see today. This discovery suggests that many of the beautifully symmetric planetary nebulae we see might be the work of unseen binary partners, adding a hidden actor to these cosmic dramas. Webb's observations of Jupiter have unveiled mysteries in our own solar system. Its infrared images show the planet's poles are racked by high-speed jet streams and colossal, complex cyclones we never knew existed. The sheer speed and chaotic interaction of these weather systems defy our current meteorological models for gas giants. The images reveal a level of atmospheric turbulence and energy transfer that is far greater than predicted, showing how even our most familiar neighbors still hold fundamental secrets about how planets work. One of Webb's most abstract discoveries relates to the reionization of the universe. After the cosmic dark ages, the light from the first stars stripped electrons from hydrogen atoms, making the universe transparent. Webb was designed to see this process. However, its early observations suggest that the process may not have been a single, uniform event. It may have happened in fits and starts, with bubbles of transparency forming and merging in a patchy, complex way. The universe didn't just turn on a light switch. It slowly and messily burned away a primordial fog. The telescope has also been used to study the smallest objects in our solar system, particularly asteroids in the main belt between Mars and Jupiter. By analyzing their composition, it has found that many of these seemingly simple rocks are far more complex, showing evidence of water ice and organic compounds. This strengthens the theory that Earth's water and the building blocks of life may have been delivered by asteroid impacts billions of years ago. But it also deepens the mystery of how such fragile molecules could be so widespread in the cold vacuum of space. In a galaxy called 2 Zwicky 96, a chaotic mess of merging starlight, Webb saw something incredible. It saw the individual points of light from globular clusters being born within the turmoil. These are ancient, dense balls of millions of stars, and we have never witnessed their formation before. The mystery is that these clusters seem to be forming before the main body of the new galaxy has even settled down. It is as if the suburbs of a great cosmic city are being built before the city center even exists, challenging our ideas of galactic assembly. Even the faintest, most distant galaxies observed by Webb present a deep puzzle of luminosity. Simply put, they are too bright. The combined light from the stars within them is greater than what our models predict for galaxies of their size and age. This could mean several things, all of them revolutionary. Perhaps the first stars were much more massive and brilliant than we thought. Or perhaps something else is generating light, like matter accreting onto small black holes. The cosmic dawn, it seems, was far from dim. The telescope's incredibly sharp infrared vision allowed it to resolve the phantom galaxy M74 in stunning detail. It mapped the intricate web of gas and dust filaments that form the galaxy's spiral arms. The surprise was the lack of stars in these dusty arms. This suggests the arms are not just collections of stars, but are more like density waves, compressing gas and dust to trigger starbirth in their wake. We are not seeing a static structure, but a dynamic, creative process sweeping through the galaxy, and the mechanics of it are still a mystery. Webb has taken the most detailed image of Pandora's cluster, a mega-cluster of galaxies already colliding to form an even larger one. The sheer number of gravitationally lensed background galaxies in this image is staggering, providing hundreds of new, distant objects to study. But the real mystery is in the distribution of dark matter that makes this lensing possible. The map of this invisible matter is lumpy and offset from the visible galaxies in ways that suggest dark matter may interact with itself through forces we do not yet understand. Closer to home, on Neptune's moon Triton, Webb's spectrographs detected frozen carbon monoxide in addition to the expected nitrogen and methane ices. This specific mix of ices is highly unusual and suggests that Triton's interior may be geologically active, venting gases from a subsurface ocean to freeze on the surface. This adds Triton to a growing list of worlds in our own solar system that may harbor liquid water, the key ingredient for life, in the most unexpected and frigid of places, expanding the boundaries of our search. The telescope revealed strange, radial spokes in the rings of Saturn, features that appear and disappear with the seasons. These are not solid structures, but are likely composed of tiny dust particles levitated above the rings by electrostatic forces linked to the planet's magnetic field. While we have seen them before, Webb's clarity shows them in far greater detail, yet the precise mechanism that creates them with such regularity remains a baffling and elegant puzzle of planetary science, a ghost in the machine of our solar system. Among the many early universe galaxies, Webb found several that are surprisingly devoid of young, hot blue stars. They are red and dead galaxies, filled only with old stars, which have ceased all star formation. Finding such galaxies so early in cosmic history is a profound shock. It's like finding a ruin from an ancient civilization that existed only a few years after the dawn of history. It means that the cycle of galactic birth, life, and death can happen on an incredibly compressed timescale, a process we are only beginning to comprehend. In the atmosphere of a superpuff exoplanet, a world with the mass of Neptune but the size of Jupiter, Webb found a flat, featureless spectrum. This indicates the planet is shrouded in an incredibly thick haze or high-altitude cloud deck. The mystery is what this haze is made of, and how such a low-mass planet can hold onto such a profoundly extended atmosphere. These worlds challenge our very theories of planet formation, suggesting there are pathways to building planets that result in objects with bizarre and seemingly impossible densities. The Carina Nebula is one of the most active star-forming regions in our galaxy. Webb's image of its cosmic cliffs revealed hundreds of previously hidden stellar jets and outflows from newborn stars. The most mysterious aspect is how these jets interact with the surrounding gas. They seem to be carving out cavities and triggering new waves of star formation, but also disrupting the very clouds needed to form more stars. It's a complex feedback loop of creation and destruction, and the balance between these two forces is a new and subtle cosmic question. Webb's instruments are so sensitive, they can detect subtle changes in the light of a star as a planet passes in front of it. By analyzing this, it has been able to create a rudimentary weather map for an exoplanet. On the hot gas giant WASP-43b, it mapped temperature variations across the surface, revealing a world with a scorching hot day side and a cooler night side, with powerful winds circulating heat. The mystery lies in the efficiency of these winds, which seem to be redistributing energy in ways our models of atmospheric dynamics did not predict. The telescope has identified the smallest free-floating brown dwarf ever found, weighing only a few times the mass of Jupiter. This object drifts alone in space, unattached to any star. How such a small object can form on its own, like a star, instead of within a planetary disk, is a major puzzle. It blurs the line between planet and star, suggesting that the universe has multiple ways of making planetary mass objects, some of which are destined to be lonely wanderers in the interstellar dark. Looking at the galaxy NGC 1365, Webb peered through the dust to the central supermassive black hole. Its spectrograph captured the signature of fast-moving clouds of gas being ejected from the black hole's accretion disk. This outflow is a form of galactic feedback which can regulate the growth of the entire galaxy by blowing away the gas needed for star formation. The mystery is the sheer power and speed of this wind, which is more energetic than theories suggested, hinting that black holes play a far more active and violent role in shaping their host galaxies. One of Webb's most beautiful images is of the Cartwheel Galaxy, a rare ring galaxy formed by a head-on collision with another, smaller galaxy. Webb's view reveals two distinct rings, a bright inner ring and a larger, colorful outer ring. The outer ring is expanding and plowing through the surrounding gas, triggering a massive wave of star formation. The new mystery is the age difference between the stars in the two rings, which gives us a precise timeline of the collision and reveals a complex two-stage recovery process for a galaxy after a catastrophic impact. The telescope has provided the clearest images of Urbig-Haro objects, which are bright patches of nebulosity associated with newborn stars. Webb showed in detail how jets of gas, fired from the poles of the infant star, slam into the surrounding molecular clouds at incredible speeds. The new data reveals complex bow shocks and turbulence patterns that are far from uniform, suggesting that the jets themselves pulse and rotate, acting like a cosmic sprinkler and painting intricate, temporary patterns onto the darkness of space. Even seemingly quiet red dwarf stars have been shown by Webb to be more violent than expected. Observations of the star TRAPPIST-1, which hosts multiple Earth-sized planets, revealed that its flares are far more energetic in the infrared spectrum than previously known. This means its planets are being blasted with more high-energy radiation than we accounted for, which could strip away their atmospheres and make the existence of life far more challenging. The habitable zones around these stars may be far more dangerous places than we thought. In studying the Tarantula Nebula, a vast star-forming region in a neighboring galaxy, Webb discovered a massive protostar that had not yet begun nuclear fusion. This object, hidden within a dense cocoon of dust, is already more than 8 times the mass of our Sun and is still growing. Finding such a massive star in this embryonic stage is incredibly rare, and provides a crucial snapshot of a poorly understood process. How these monsters accumulate so much mass without blowing away their own natal clouds is a key unsolved mystery in astrophysics. The telescope has been used to hunt for rogue planets, worlds that drift through the galaxy untethered to any star. By using a technique called microlensing, it has found several candidates. The mystery is their sheer number. Early results suggest there could be billions of these dark, lonely worlds in the Milky Way, perhaps more numerous than the stars themselves. This opens up the profound question of where they all came from, and what stories these cosmic orphans, forever cast out into the cold and the dark, could tell us. Webb's precise measurements have allowed astronomers to refine the ages of the oldest known star clusters. In several cases, a baffling paradox has emerged. The calculated age of the star cluster appears to be slightly older than the calculated age of the universe itself. This is, of course, impossible. This age paradox points to a fundamental flaw in one of our 2 foundational measurements. Either our understanding of stellar evolution is incomplete, or our model of the entire universe's history and expansion needs a significant revision. In the famous Eagle Nebula, Webb's image of the pillars of creation showed them to be less like pillars and more like ephemeral translucent curtains of gas being eroded by the fierce radiation from nearby massive stars. The mystery revealed by Webb is the sheer speed of this erosion. The pillars are evaporating before our eyes on a cosmic timescale. We are witnessing the final, fleeting moments of one of the most iconic structures in the night sky, a beautiful monument to the universe's constant and unrelenting change. The telescope investigated a rare class of galaxy known as luminous infrared galaxies, or LIRGs. These galaxies are shrouded in dust and glow incredibly brightly in the infrared, a sign of frantic star formation. Webb's vision pierced the dust and revealed that many of these are not single galaxies, but are in the final stages of a cataclysmic merger between 2 or more galaxies. The new mystery is how efficiently this process channels gas into the galactic cores, igniting a starburst of activity that is almost incomprehensibly violent. Webb examined the atmosphere of Mars, looking for trace gases that might hint at geological or even biological activity. While it did not find methane, a key target, it did map the global distribution of water vapor and carbon dioxide with unprecedented detail. This data revealed unexpected microclimates and weather patterns, showing that the thin Martian atmosphere is far more dynamic than we knew. It provides a new, deeper understanding of the planet's past, and a new baseline in the ongoing search for signs of life, past or present. A very specific type of supernova, called Type Ia, is used as a standard candle to measure cosmic distances. Webb observed the remnants of one of these explosions in a nearby galaxy. Its infrared capabilities allowed it to analyze the composition of the ejected material, revealing clumps of elements like iron and silicon. The clumpy, asymmetrical nature of the debris challenges the standard model that these explosions are perfectly uniform, introducing a new uncertainty and a new mystery into the very foundation of our measurement of the cosmos. The telescope has observed so-called green P galaxies, small, compact galaxies glowing with an intense green light from ionized oxygen. Webb has shown that these galaxies are modern analogs of the type of galaxies that likely existed in the early universe, responsible for reionization. The mystery is why these galaxies are so incredibly efficient at producing high-energy radiation. They are small, but they punch far above their weight, giving us a laboratory to study the cosmic dawn right here in the present day. In a distant planetary system, Webb observed the direct thermal glow of an exoplanet and saw its light dim and brighten as it orbited its star. This allowed astronomers to create a rough map of its cloud cover. The resulting map was strange, showing large, patchy clouds that form and dissipate on a timescale of hours. This indicates a dynamic, chaotic weather system on a world hundreds of light-years away. And the chemical composition of these fast-moving alien clouds remains an intriguing and unsolved puzzle. The telescope's deep field images are not just pictures. They are core samples of cosmic history. In one such image, astronomers found a chain of galaxies, all at the same extreme distance, arranged in a long, straight line. This structure, dubbed the cosmic vine, is far too large and organized to be a chance alignment. It suggests that the first galaxies may have formed along massive, dense filaments of the cosmic web, like pearls on an invisible string, hinting at a far grander and more ordered structure to the early universe than our theories predicted. One of the most fundamental mysteries is the nature of dark energy, the force accelerating the expansion of the universe. By observing distant supernovae with greater precision than ever before, Webb is helping to refine our measurements of this acceleration. Early data confirms that the expansion is indeed speeding up, but it has also opened the door to more exotic theories. The data is so precise that it may be able to distinguish between dark energy being a constant property of space or something that changes over cosmic time. Webb's gaze into the heart of the Orion Nebula revealed a wealth of protoplanetary disks, the swirling disks of gas and dust around young stars where planets are born. But it also found many of these disks are being actively destroyed. Intense ultraviolet radiation from massive nearby stars is boiling away the gas and dust in a process called photoevaporation. We are watching solar systems being murdered in their cradles, a discovery that adds a new level of cosmic jeopardy and chance to the story of how planets, including our own, come to be. The telescope has discovered galaxies in the early universe that appear to have a quote-quote structure, a dense line of stars and gas running through their center, just like our own Milky Way. The formation of these bars was thought to be a slow, evolutionary process that happens in mature, stable galaxies. Finding them so early on is yet another chronological impossibility that defies our simulations. It suggests that the internal dynamics of galaxies can evolve much faster, driven by forces we have yet to properly model. On Enceladus, a moon of Saturn known for its icy plumes, Webb did not just confirm the presence of water vapor, it found the plume extends thousands of miles into space, far larger than previously imagined. This vast plume is actively feeding Saturn's E-ring with icy particles. The sheer volume of water being ejected hints at a massive and long-lived subsurface ocean, making this small, icy moon one of the most compelling and mysterious places to search for extraterrestrial life in our entire solar system. The light from the most distant quasars, bright galactic cores powered by supermassive black holes, must travel through intergalactic space for billions of years to reach Webb. Along the way, this light is absorbed by the sparse atoms of hydrogen in the cosmic web. By analyzing this absorption, Webb has created a map of this nearly invisible material. The map reveals that the web is not uniform, but is filled with vast, unexpected voids and dense knots, a lumpy texture that is another deep mystery for our cosmological models to explain. Each new image, each spectrum of light, each piece of data, sent back across a million miles of silence, seems to follow a simple pattern. For every old question that is answered, at least two new, deeper, and more beautiful questions are born. The telescope was not built to end the mystery of the cosmos, but to deepen our appreciation for it, to show us that the universe is not a solved puzzle, but an infinite story that is still unfolding. The new mysteries revealed by the James Webb Telescope are perhaps its most important discovery. They remind us that our knowledge is a small island in a vast ocean of the unknown, and they invite us, with a sense of profound and meditative calm, to keep looking up, to keep wondering, and to cherish the magnificent, unending enigma of the stars. One of the great quests for Webb is to study the reionization of the universe. After the cosmic dark ages, the light from the first stars stripped electrons from hydrogen atoms, making the universe transparent. Webb was designed to see this process. However, its early observations suggest that the process may not have been a single, uniform event. It may have happened in fits and starts, with bubbles of transparency forming and merging in a patchy, complex way. The universe didn't just turn on a light switch, it slowly and messily burned away a primordial fog. In studying the Tarantula Nebula, a vast star-forming region in a neighboring galaxy, Webb discovered a massive protostar that had not yet begun nuclear fusion. This object, hidden within a dense cocoon of dust, is already more than 8 times the mass of our Sun and is still growing. Finding such a massive star in this embryonic stage is incredibly rare and provides a crucial snapshot of a poorly understood process. How these monsters accumulate so much mass without blowing away their own natal clouds is a key unsolved mystery in astrophysics.